So welcome again to Anagon Live. Today is day 17 and part 1 has been released already 35 minutes ago or so. I am a little bit later, just like the day before, because day 16 was quite tricky and I spent a lot of time on it and I haven't even finished it yet. But I am quite near the solution. I have the algorithm figured out. There might be a small hiccup in my implementation. I'm not sure yet. We'll have to see about that after day 17, because I do want to see what day 17 is about, and I might need a little bit of hint on day 16. And as everyone is still working on day 17, I think I'd rather just join along and do that. And Emmy, you're mentioning that Alex got to the top of the leaderboard, and it is the case indeed. Alex, you're right on the top. Congratulations on that. And does that mean that you're also high on the leaderboard list, the global leaderboard list? Let's have a quick look before we continue doing day 17. So we have the global leaderboard and you're 20 globally. Wow, very nice. That means you jumped up a few notches than before. And oh, you were 20 for this puzzle. Wow, that's super fast. And so on the global leaderboard, you are, let me see if I can find you. You're here on 35. So you have dropped quite a bit. I hope you're gonna be able to stay at least above the end of the list so that we can admire your great results for the whole year to come. I'm not gonna be on that list. I am not so fast, but I am persevering and finishing all of the puzzles with or without hints. So day 17. Set and forget. An early warning system detects an incoming solar flare and automatically activates the ship's electromagnetic shield. Unfortunately, this has cut off the Wi-Fi for many small robots that, unaware of the impending danger, are now trapped on exterior scaffolding on the unsafe side of the shield. Okay, and to rescue them we'll have to act quickly. The only tools at our disposal are some wired cameras and a small vacuum robot currently asleep at its charging station. The video quality is poor, but the vacuum robot has a needlessly bright LED that makes it easy to spot no matter where it is. A very recognizable vacuum robot, that is. An encode program, which is called ASCII, provides access to the cameras and the vacuum robot, so it does both things. Curious how it is going to be able to operate both cameras and the vacuum robot. Currently, because the vacuum robot is sleeping, you can only access the cameras. Okay. So, and then running the ASCII code on your Intcode computer will provide the current view of the scaffolds. Congratulations, Hans, for finishing part 1. And this output purely coincidentally as ASCII code. This is output as ASCII code, so the numbers are actually ASCII characters. And we are given the ASCII codes for the characters that are most likely going to be used by this program. So within a line, characters are drawn from left to right. And in the camera output, a hash represents a scaffold, a dot, an open space, and a robot is visible using 4 different kinds of arrow characters, depending on which way it's facing. And when you draw it this way, the robot is always on a scaffold, and if it ever walks off of a scaffold, it will fall through space uncontrollably and it will be visible as an X. And being on a scaffold, what does that mean exactly? It means you're going to be attached or you're going to be vertically above it. That's the question I have right now. In general, the scaffold forms a path, but it sometimes loops back onto itself. Oh, so you're above it, so kind of like on the same position as a scaffold. Okay. Suppose you can see the following view from the camera. So you're actually viewing it from the top, so to say. Here the robot pointing up is facing up and sitting at one end of the scaffold near the bottom right of the image. The scaffold continues up, loops across itself several times, and ends up at the top left of the image. Okay, the first step is to calibrate the cameras by getting the alignment parameters of some well-defined points. Locate all the scaffold intersections for each its alignment parameter is the distance between its left edge and the left edge of the view, multiplied by the distance between its top edge and the top edge of the view. I don't know what that means, like conceptually. So we have alignment parameters that are well-defined points. We need to locate scaffold intersections. That is straightforward also. And the alignment parameter is the distance between the left edge of the view multiplied by the top edge distance. Okay, so the top left intersection is 2 from the top and 2 from the left, so the alignment parameter is 4. Yeah, but that's only for one intersection, right? So to calibrate the cameras, you need the sum of the alignment parameters. In the above example, this is 76, and I feel that probably this alignment parameter is not going to be used for anything other than just proving that we are able to parse the input. So let's download our puzzle, which is our Intcode computer's input, and let's get it from the screen and go to day 17 and write a file, a plain text file called input. What was this? Plain text. Oh, text. No, it's just called file. Input.txt with this data in it, and we're going to make a Python file. As you can see, I'm not really prepared with templates and anything. I just need to start from scratch at the start of the day. So we're reading the file, which is file, or was it open? No, it was open. Every day I forget. Day 17, and we're going to read the lines, or actually I'll use a handler. So with open as file handler and file handler.read lines, and that is actually a single line, and that means we don't need to trim it because our input doesn't have a new line character. We can just split it right away by comma and get. Oh man, I'm making the same mistake as before. I don't have to actually parse the file because I have an Intcode computer for that. So our Intcode computer from day 9 can be used for this. And we can just tell it to read the file right away. So that's day 17/input.txt. And then we're going to run it, run program, and we don't need to provide input. And then actually we need to handle the output. That's all we need to do. So at the end we get output, and those are characters. That is the computer's output, and it is printing from left to right, row by row. So that means basically we can loop over the characters for C in characters. If C equals a new line character, and that was actually well, what we also can do is use actually a CHR or C, that is an actual character, and then we can compare it with new line, maybe with double quotes. I hope that works. Let's try in the Python console if that works. So character code of 10 is a new line, and can we check it like this if it's equal? Yes. I was just confused because my editor doesn't highlight /1 as a special character. So this means a new line. It means that our Y position is going to increase, and otherwise we have an X position, and X is going to be reset to 0, and every character we're going to go 1 to the right, but only at the end of the loop. So now we have an X and Y position, and we are going to see if we are now going to be at, hold on. When we have a new line, we're also going to continue to the next iteration. And if we're not skipping, that means that we have probably a dot or a hash, and we need to calculate the intersections. But hold on a second. The output goes from left to right, and that's it. So probably we are not having line, we don't trace lines at all, but we need to find a position that has 4 walls around it. So like a a piece of scaffold with one up, one down, one left, and one right. So let's make a grid first. And a grid is, I'm gonna keep it as a list of points. That's it. Well, yeah, maybe a set actually. So let's call it scaffolds like this. And if our current character is actually a scaffold character, that's a hash, and we're going to append it to the set like this with add, and we're going to add a tuple x and y, but we have to say that it's one parameter and not two parameters. And now we have our scaffolds, and let's see if that runs and if we get something that makes sense. That looks like I'm debugging my program, and that's not what I want to do. So we're turning off debug mode, and now we get a list of positions, and that's quite a big list. And then after that we're going to loop over every position and see if the upper, down, lower, left and right neighbor are occupied or not. So for each position in scaffolds, we need to check all of the locations, and let's actually unpack it right away. And let's make a list of all the neighbors that we might find. So neighbors is a list where we have basically a relative position of 0, 0, but then we're going to adapt one to the right, one to the left, one up and one down. And for each neighbor we need to check. We need to find if we have 4. So we're assuming that we have 4, and if we don't find the neighbor, then we don't have 4, right? I noticed that the music has paused, even though I have autoplay on YouTube, but it just doesn't like me to play music in the background apparently. So here, some other nice Christmas songs. I'm going through this very fast. I hope to get a little bit of good points today. So for every neighbor in the neighbors, we're going to see if we're missing any neighbors. If we're missing any, then we don't have an intersection. So intersection is true unless we don't find a neighbor somewhere. So the neighbor xy is going to be the current xy. Ah yeah, so the delta x and delta y, we can extract it straight from the neighbors. So it's x plus dx and y plus dy. That is the neighbor's position. And if that one does actually occur in the scaffolds list, then we have a possible intersection. And if it doesn't, then we have definitely no intersection. So our intersection is not found, and we can break out of the loop and stop trying. So now if we still have an intersection after testing everything, then we found one. And so if intersection, then we found it, and we're going to have to probably keep a list of it, or to calculate the alignment, it is actually the sum of all the alignment parameters. So and that sum is called, okay, the sum of alignment params, which is 0 first. And so if we found it, we're actually going to, the distance from the left and the top, that is actually the alignment parameter. So that means we have to calculate it relatively to the top. So we have a relative x multiplied by a relative y, and that is what we're going to add to the alignment parameters. But relative x and y, we need to calculate it. We need to first know what the left side of x, the left and top side is. And the Christmas music is now very much distracting me because it is no longer instrumental as I had requested to my YouTube playlist. It is festive pop, indie Christmas, something I'm definitely not interested in listening to. So let's have a look at some alternative. Christmas jazz is what I want. And previous time, the second, yeah, maybe this one. Yeah, that is a little bit more nice and relaxing. Alright, so continuing onwards, we need to calculate the relative alignment, and the relative alignment will basically be, we need to know the minimum x value in all of our scaffolds, and that is going to be the minimum of scaffolds, and we use a key for that, so that when we get a position, that we are going to use only the first dimension of that. A lambda. Python seems to complain about something here, but lambda. Okay, I guess there was a typo in there. And for x we're using for y we're using the second dimension for every point. And that is the minimum. That's all we need basically. And Rx is not the right term, it is the min x and the min y. And so the Rx is actually the position relative to the minimum position. So if the minimum position is the smallest one, then we're going to get the relative one by taking the x position minus the one that is probably smaller, or should be smaller, like this. So now we get positive numbers for those numbers, and that is it. We need to print the alignment parameters, and we get a problem somewhere here. So where do we get a problem? The min x says that it's actually, oh yeah, it returns a tuple instead of the actual value. So what can we do about that? We can take the first item, of course. Yeah, that is one way to do it. And for the y, we need to take the second dimension and not the first one. So now we get a number, and let's see if that is right. And it's right. Okay, good. So now we can go to part 2. Now for the tricky part. Notifying all the other robots about the solar flare. The vacuum robot can do this automatically if it gets into range of a robot. However, you can't see the other robots on the camera. So you need to be thorough instead. You need to make the vacuum robot visit every part of the scaffold at least once. The vacuum robot normally wanders randomly, but there isn't time for that. Instead, you can override its movement logic with new rules. Force the robot to wake up by changing the value in your ASCII program at address 0 from 1 to 2. Okay, so we're going to wake up the robot. Let me actually commit this code very quickly so that I will be able to make any reversions if I need to. Not run, I need to do git and then add. Actually, git and commit. That is day 17, part 1. I'm happy that part 1 was easy to solve. Now for part 2. Normally it wanders randomly, but we need to override its wakeful mode. So address 0 is going to be changed into it's going to change from 1 to 2. Okay. So the program actually computer.positions in position 0 will be 2. Wake up the robot, and then we will be automatically prompted for the new movement rules that the vacuum robot should use. So you know what, I'm actually going to rerun the robot. I'm going to reload it after doing this first section, because I want to be able to have access to all of the grids. So like this. We just run it again. And I will be prompted for the new movement rules that the vacuum robot should use. The ASCII program will use input instructions to receive them, but they need to be provided with an ASCII code, and each line of logic with a single new line. So we actually have to write code that will be provided to our robot. But how? First, you'll be prompted for the main movement routine. Okay. The main routine may only call the movement instructions A, B, or C. Okay. So we have a main routine, and it can call A, B, and C. Supply the movement functions to use ASCII text, separating them with commas. Supply the movement functions to use as ASCII text, separating them with commas. Okay, so I need to actually convert every character into ASCII and then give it to the robot. Alright. For example, to call A twice, then alternate between B and C 3 times, you provide it like this: AA, BC, 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 and then a new line. Okay, so it's a little instruction script. Then you will be prompted for each movement function. Movement functions may use L to turn left, R to turn right, or a number to move forward that many units. So basically we have the map, we know how to move, we can calculate that without the robot, and then we just need to give it a long list of instructions, right? The movement functions may use L to turn left, R to turn right. Ah, okay, actually, so we have kind of macros, we have like so we can give it an instruction like go 10 forward. That could be a movement function. And then we can reuse that over and over again in our final algorithm or strategy. So movement functions can go left, right, or go forward. And you separate them with commas and end with a new line. So moving forward 10 units and then left and so on. So far I wouldn't think that we have a big problem, because we could just make 3 functions, one that turns left, one that turns right, and one that goes forward. But we would only have a problem if we have a space limit. And that's probably what is going to happen. Finally, like a space of how big the programs can be. Finally, you will be asked whether you want to see a continuous video feed. Provide either Y or N and a new line, yes or no. So we have first main routine, then we have A, then we have B, then we have C, and it ends with a new line, and that is like left, right, or what else was it? Left, right, and a number like 13 plus a new line, and that can be repeated many times like some kind of number. Can also be repeated, same for those, and then finally we get feed yes or no with a new line. Now I'll indicate it like this: it's L or R or N, repeated multiple times. Okay, we separated, yes. So for example, to move forward 10 units, then left, then forward 8, and turn right, finally move forward 6 units, then you do like 10 forward, then left, and 8, then right, then 6, then a new line. And alright, enabling the continuous video feed can help see what's going on, but it also requires a significant amount of processing power and may even cause your encode computer to overheat. Okay, but why would we need the video feed? Due to the limited amount of memory in the vacuum robot, the ASCII definitions of the main routine and the movement functions may each contain at most 20 characters, not including the new line. So that means that between 0 and 20 characters. For example, consider the following camera feed. In order for the vacuum robot to visit every part of the scaffold at least once, this should be the path. Without memory limit, you could just supply this whole string to function A and have it call the main routine. Have the main routine call A once. However, you'll need to split it into smaller parts. Okay, so because we have some kind of repetitions, that is what we can use to optimize our program. Of course, scaffolding outside your ship is much more complex, and as it finds other robots and notifies them of the impending solar flare, it also can't help but leave them squeaky clean, collecting any space dust it finds. Is that relevant? Once it finishes the programmed set of movements, assuming it hasn't drifted off into space, the cleaning robot will return to its docking station and report the amount of space dust it has collected as a large non-ASCII value in a single output instruction. Wow, okay, so it makes it squeaky clean. It means that if it passes over a position twice, it's not going to actually, what was I gonna say? If it goes over a position twice, it's not collecting dust twice. And so first I thought maybe that means that actually we don't need to find those robots, we're just going all over all of the scaffolding, and that is basically the number of positions, and that is how much space dust we have collected. It would be very silly if that is actually the answer. As long as the other robots are not on or are possibly on intersections, then I can just count the number of hashes. You know what, let's just try for fun to see if the number of items it would collect is basically exactly the same as the number of positions on the scaffold. It's not very likely, but let's see. And we need to find the shortest way to visit all of them, and that sounds like a traveling salesman problem. That is not trivial at all. Okay, we could, well, brute forcing it is probably not possible, but let's see. Okay, so I want to make a loop and print the entire map. So we are going to loop from min x till max x. So maybe I'll also calculate the maxes. And that's all we need to do. No, we need to make it into max. Like that. And we're going to draw everything for y in range min y till max y plus 1. And same for x. Min x and max x. And then we're going to print the character c. Let's see how we can do that. The character c, and c is actually, wait, it is a hash actually. So if x and y is in the scaffolds list, okay, I guess I have to use explicit tuple here. Then we're going to print a hash with no line ending, and otherwise, well, you know what, let's just do it like this, just inlining that. If xy is in the scaffolds, and otherwise we'll print else a dot, I guess. Yeah, almost like this. So now we have a map. No, not yet. We need to also print new lines. Now we do have a map. Okay, it looks a bit complicated indeed. Can we find any patterns right away? We can see long stretches, but I see that. Okay, let's just start somewhere and see how it goes. So this one actually seems to go into space. We go left a bunch of times, up, left, 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 right, left, right. Okay, so we're mostly going left, right, left, right, left, right, but sometimes we go left twice or right twice. That's how it seems. And so now it's a little bit difficult to see how many characters we're moving. We're moving 10. And then we're moving 2, 4, 6, 8, 9. So 10 and then 9. And then 7. And then 7. And then... Okay, maybe I can actually draw. Maybe I can actually make annotations on this thing. How can I do that? Can I copy it somewhere? Not sure. Okay, I'm going to see what I can do to make this work. Maybe like this. I'm going to put my whiteboard next to the output. It's a little bit small, but it might be possible to see it. Like this. So now we have the whiteboard on the top, and it doesn't fit entirely on the page. Maybe like this. Yeah, that would almost work. Let's see if I can make it work. No, I can't. That means I'm going to put it here. Just a bit of a technical challenge here. Okay, so you can actually see my whiteboard, and I'm going to make some notations. So we have a map and it goes to the left, and I want to know how many, and it went to the left. I can count it in the console, 10 characters to the left. So 10, and then we go up and it was 9. I'm doing this to just see if there is a pattern that I can recognize. Then it's 7, and then we go up again. And how many was that? I think it was also 7. Well, it depends a little bit on how you count. I guess if you count from starting here, if that's really where you start. Actually, we don't know where we start. Where do we start? Hold on a second. I printed only the scaffolds, but I didn't print where the robot was. So I think we need to keep track of the robot, which is going to have a variable none. And then if during the loop we're actually finding a robot, how do we do that? We run the entire program, and if we see a hashtag, it's a scaffold. But if it is actually a carrot, we're facing up. But maybe it's not a carrot. I'm not sure if we start up or left or right. I think it could be any of those. So let's try it like this. So we have up, down, right, and left. And if that is the case, then the robot's position is XY. So I need to define the robot before. Don't have to, but I just like to do that. Now we have a robot position. So here, if we are in the scaffolds, then we're printing a hashtag. And otherwise, what happens if we have a robot? Can you do an inline elif? You probably can't. But let's see. Elif robot. No, I wouldn't know how to finish this. So I am actually going to undo it and write it in a simple if-else statement. So if XY is in the scaffolds, then we're printing a hashtag without an end. And then if XY equals the robot, then we're printing we also need to keep track of the robot's direction. So for now I'll use an @ sign, so we at least know where the robot is. And something went wrong. I'm printing both a scaffold and a robot, I think. Oh yeah, and if it's not in the scaffold and it's not a robot, then we have to print a dot. That is what's not going right at the moment. And equals nothing. So that looks like something, and our robot is nowhere to be found. And I realize why, because we are comparing with any of these positions, and no, but that looks fine actually. So let's see if our character is anything else than a scaffold. Then what do we get? Maybe we can print it, or maybe we can break like this. So we run it and we break. Oh, we don't actually break at all. So that means that all of our characters are scaffolds. So why is that? You will get the current view of the scaffolds, yeah? And the vacuum robot is visible as one of those characters, depending on where it is. The robot is always on a scaffold, and if it walks off, it begins tumbling uncontrollably, and it will be visible as an X. Okay. But I don't see anything else. So I get all the characters, and if it's a new line, I go to the next line. If it's a hashtag, I do this, and otherwise I say pass, but I'm not breaking. Why is that? I'm not breaking and I'm not printing any robot, so it really seems like we don't get any robot in the output. So I'm going to break and look at all of the characters in the computer's output. Maybe it's because the robot is not awake in this version of the computer. So the characters, it looks like a list of many things. It is mostly 46 and 35. And those characters are, what are they? They are, 35 means a hash and 46 means a dot. Then if that's really the case, then why don't we break here at all? Maybe it's because pass doesn't work or something. So let's actually break on the print statement. Let's see how it goes. Okay, now it is actually breaking. Not entirely sure why. And I see my clock is completely out of sync. It's so annoying. I don't know what OBS is doing these days. Let's try to get it resynced. Maybe if I click here. Maybe like this. Yeah, now we have a better clock. Although, yeah, it's 10 past already. So, we are breaking, and we're really not breaking here. That doesn't make a lot of sense. We are not breaking there. Wow. So, I don't know how that works. I have a feeling that maybe pass is kind of removed from the compiled code, and that basically you cannot break there because it doesn't actually consist of a statement. So we have something else, and that something else is character 46, which is a dot. And if we have a robot, which we should have, let's maybe break when it's anything other than 46 or 35. So if the Arcanian Archer has solved already part 2. Nice, that's 2 people on the board right now, and most of us have finished part 1 and working on part 2. So if the character C is not a hash and character C is not a dot, then let's break. And let's then keep running the code. And we're stopping now. Oh, actually our breakpoint has an error in it because it's CHR and not char. So we're done and we keep running it. And we're printing a lot, and now we're breaking finally, and we get character. What character do we get? We get 94, and that is a caret that goes up. So now my question is, can you do something like this? Hello, foobar, and get true. Yeah, you do get true actually. So that means that also we should be able to get this, yes, and we have an X and a Y position for the robot. And so when we are done, we should actually have stored the robot, which we do, and then we should be able to print the robot also. But why didn't I see any robot? Maybe there is a robot somewhere, or maybe it's because I'm first checking for scaffolds and then only then checking for the robot, but the robot has priority. That's why it didn't work. Okay, so now we know what our map looks like, and we have a robot. Where is it? Oh, I still don't see a robot. So if we have a robot, hold on. Okay, we don't have a robot. Why is that? Let's actually break there. So robot XY is going to be stored at 52 and 26. And yeah, that is the absolute position, or it's actually relative to where we started and not so much relative to the top left of the screen. Well, it is. I just realized that I was doing something very weird and unnecessary. I was calculating the minimum x and the minimum y, but that is actually 0 because we're not drawing lines on the screen like tracing. That means we don't get like, how do you call it? Well, we don't increment our position at all, and then we have to figure out what the maximum position is. No, it's we're just drawing line by line. So basically, if we would have looked at the first line, we would know how long every line is, and the number of lines is just the height. So this whole min-max thing is really not needed at all. And also the relative distance from every intersection is also not needed at all, because it's just x and y. So I just realized that right now. So if you are going to re-implement this, you can totally skip that part. And I have x and y at 52 and 26. I'll just write it down. Oh, that looks funny. Not sure what that means. And then it means that we should have a robot when we reach 52 and 26. So min y is not calculated at the moment. So we run until the end. And then min y is 0, as I said, and max y is 38. Okay. And the x max position is 51. But it says that our robot is at 52. But we are actually rendering it. So how is it possible that, for the max, I'm only checking the scaffolds and not also the robot? Okay. So it means that I need to take into account also the robot. Oh well. Robot X. Well, I already know the answer. I could just basically write it there. But I'll just do it this way so it would work on other people's input as well. So the maximum y is the max of whatever you get in the scaffolds and also the robot's y position. Now we actually would render a little bit further, and that means that there's also a scaffold underneath where the robot is. So if we are a robot, then we need to add it also. It's important to notice. And we're running it, and now we see a robot somewhere. Do we or not? I don't see it. I don't see the robot. And are we now iterating a bit more than before? So the robot's max position is going to be, it's going to be 52, and then we run and we see max x being 52. So that is fine. And the robot, oh yeah, it's a cool problem, right? So far it's fun. I like anything that is kind of graphical or has mazes in it. So our robot is at 5226. Those are the x and y coordinates. And our range is from 38 till 52. So we do iterate over it. And why don't we see our robot? Maybe I do. Maybe it is actually rendered. I just don't see it or something. Yeah, we actually do print it. So there it is. So maybe what I want to do for today is Python doing some color coding. Color output should not be too hard. Actually, I know you can do it. We can basically use an escape character like 33 or something like that. And then use, what was it? Like 42 M. I'm not exactly sure. Something like that. And then you can basically get colors, but let's see how it works. Oh yeah, that was actually kind of correct. But maybe you cannot use print. B colors, okay. Oh yeah, 033. Like that. Yeah, now we actually get colored output, and then this is a very ugly color actually, so I would like to use OK green from the example here. And then I'm gonna close this because it's way too bright. And then to reset the color, you just need to do an escape code with a bracket and do 0M, and then you've reset the colors. So now you can see that actually the robot is there. You ended up doing part 2 manually. That is also ingenious. And you were actually the first one to solve it, so why not? Why not actually do it manually? And Arcanian Archer also the same. But wow, lol, that's really funny actually, and surprising. Yeah, there is an instinct that I sometimes have, is like, why not? Why use code if you don't have to? It is not a very long line actually. But we do need to know if we have any robots on our path. So I wanna... Oh, Nubali also. Oh, you guys. Wow. Oh, man. I feel like I missed out a bit. You did part 1 manually, and you're trying to see if you can make 2 work manually, but you're finding it tricky. Okay. I did part 1 automatically. Oh, well, so proud of that right now. Okay, so how does it work? And what does it say? Facing up, sitting at one end, yes. And it is here, and we don't know where it's facing. So I'm not sure if I actually need... Yeah, because the funny part is you have to write an entire program and like figure out the patterns and make it better, make it fit in 20 characters. It's really complicated compared to actually just going over the map. So maybe I'm gonna try it manually as well. But there are still some things that we need to do, because we need to know if we find any robots, or we don't know where they are and we just have to visit all of the spaces. Was that actually what they were saying? Part 2, excuse me. So visit every part of the scaffold at least once. Well, oh, we don't have a traveling sales problem. We have to visit every part once. So that means we just need to calculate the number of scaffolds. No. Did I try that? I said I was gonna try it, but I think I didn't. So the number of scaffolds is like this, and we're just running it. Oh. And the number of scaffold is 279. And what was the first question? Okay, and then that is it, right? No, it's not right. It's too low. But does it collect space dust multiple times then? When it's going over it? They aren't worth 1. Oh, is it mentioned? So you have some path. Okay. Let's see. As it goes around and finds no robots, it's collecting any space dust it finds. Once it finishes the programmed set of movements, assuming it hasn't drifted off into space, the cleaning robot will return to its docking station and report the amount of space dust it collected as a large non-ASCII value in a single output instruction. As a large non-ASCII value. Ah, you're gonna go to sleep. Okay, that's great. Have a good sleep and a good job solving the puzzle. You can have a good rest. And Alex, you're saying you can't cheat unless you disassemble the program. But I think I'm confused about the space dust part. It says it leaves... Does it leave the robot squeaky clean or what? Or the scaffold? Collecting any space dust it finds. So maybe it's about counting the number of robots then, basically. Yeah, but the space dust it's collecting, is it collecting it from every robot it encounters or from every part of the scaffold? Yeah, don't worry about the robots or the dust. But still, let me read again what I'm supposed to do. So we need to visit every part of the scaffold. Okay. but the answer requires me to tell the number of space dusts I collect. So I do need to know what they mean exactly by space dust and when it is collected exactly. Oh, that's what you say. Ah. So it's going to tell us how much it collected. Ah, okay, so we actually don't know whether or not it collected anything. It's just reporting. Okay, in that case we do have to run it, but then how can you manually solve it? You can manually solve it by first tracing the path that you need to take. And then you will get an output. Okay, well that makes sense, but then solving it manually still means that you are going to have to give those instructions to the robot, and you do have to define those routines, right? So we can say, yeah, okay, so let's continue with what we were doing. We were actually looking at the input at the puzzle and just taking notes of where we're going. And maybe instead of counting the distances and trying to find a pattern in the distances, I'm going to actually write down the instructions that we are supposed to give to our robot. And I think that we might start with our robot facing left. So let's keep a list of directions, or actually I'll just use this one right here. And I want to make it in such a way that I can just add one to go right, for example. So up, right, down, and left. And then we have a direction. And the robot's direction is called dir, by default none. And we're saving the direction. And the direction is basically the index of all of the directions, the character in all of the directions. Like this, and that is the direction. And then when we print the robot, we can actually use that direction to visualize it in a bit better way. Maybe I'll use string formatting for that, like this. And the direction will be passed into the directions array, like this. And then modulo, no modulo. So we have 0, 1, 3. So we're facing up, that's important. So then we can look here to the right. So okay, we go first left, and a certain number of times left, and it was yeah, interesting. Now I'm not counting the robot, and that's actually correct. So we go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and it's 10 characters. So I can use the number of characters also. So left 10, then we turn right, of course, and we go up 1, 2, 3, 4, 5, 6, 7, 8 times up, and we go. Not sure how I will find the pattern if I write it all in a row. Maybe like this. Right 8, and then we go left, and it is 6 characters. And then we go up 1, 2, 3, 4, 5, 6. And then we go left 1, 2, 3, 4, 5, 6, 7, 8. Left 8 and down. 1, 2, 3, 4, 5, 6, 7, 8. And then also 8 to the left again. Oh wait, that is not left, that is called right. So I need to use directions relative to the robot's orientation. So it's right, left. So we first go left, and then we go right, and then we go left, and then we go right, and not up. Up is not a direction. And then after we go up, we go left, and then we go not down but left. That looks like an L. And then we go right. Okay, and then after 8 right, we go down. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Down was left again, so 10 left. And then right 1, 2, 3, 4, 5, 6, 7, 8. 8 to the right, and then we're turning left. Probably it's also 8. I think I was here. 1, 2, 3, 4, 5, 6. And then we go right, and that is 8. And right, and that is also 8. And then we go left, and it is 8. No, it is not 8. It is 7. Or actually 6. And we go right again, and that should be 10 most likely. Right. And nog one more time left. And then right. How many times? 8. Right 8, and then left 8. No, 6. Man. Nog einmal. Yeah, I was going to speak Dutch actually. Some Dutch slipped out in the early morning. It's nog een keer, nog een keer. It's very similar to German. Now I lost a bit of track where I was. I went right twice, that was this part. And then I go left. No, right twice was this part, and then I go left. And then I go right. Then I go left, and then I'm up here. Early morning Dutch, yeah. 1, 2, 3, 4, 5, 6. Right 6. 1, 2, 3, 4, 5, 6, 7, 8. 8 to the left. Oh, this is so boring. Oh my god. 1, 2, 3, 4, 5. Wait a second. 1, 2, 3, 4, 5, 6, 7, 8. So we went left again. 8. Right? Yeah, we did. And then we went right. And again. 1, 2, 3, 4, 5, 6, 7, 8. And this is also 8 characters to the right. And then we go left 6 times. Probably there's already a strong pattern here and I don't have to actually do it, but I'm just gonna finish it like this. And then we go left. Oh, we go left 3 times. Okay, why not? 10, and then another times left 8 times probably. Here, yeah, up. Another times left 8 times, and then right. Am I done? No, not done yet. It still takes a lot of steps. 8 characters to the right. 8 characters down. And then left 6 characters. Oh, man, this is so big. And then we're going up. And that should be 10 because we have only 10 when we go up. And, well, no, we have... yeah, basically we have the numbers 6, 8, and 10. Okay, and then we're here and we're going to the left and it's also 10 characters. Again, turning left and going down 8. Going again left. How many? 8. And then we're going right. And that is the last bit. And that is 1, 2, 3, 4, 5, 6, 7, 8. Right, 8. Okay, there we are. So actually I realized now that there are no patterns. There are actually no patterns. The only pattern is basically a single instruction. So, no, that's not true. That is not true. We do have patterns and we need to use patterns. So we have the 3 different... How was it again? So we have 3 different methods that we can use. And in each method we can provide a pattern. And the limit is 20 per method. That is okay. And now let's look at the patterns. So, what do I see when I look at it right away? I don't see a lot of patterns. I do see 4 times 8 in a row. That is happening here. I do see 4 times 8 in a row here. And I see it also somewhere else? No, nowhere else. Maybe here, but I think probably it's not. We shouldn't count that one. I see 3 times 8 in a... No, that's not the same pattern. Because this is left, left, right, right, left, left, right, right. And here we have left, left, right, left, that's different. Another pattern is maybe 10-8-6. Do we see that anywhere else? 10-8-6. 10-8-6. Okay, so that can be a pattern maybe. And here we have 10-8. That's nothing. That's not helpful. What else? Well, we have 8-8. You know what? I'm gonna use different colors for the different patterns. 10-8-6, 10-8-6, and that was not it. Here's another one. I'm not really sure what is the right way to find patterns easily. You can of course run some code to do it. That would be fine technically. We have 8-8 that could be used. 8-8 is also here. Yeah, and of course here, if you would look at it from the other side, here's 8-8, here's 8-8, and here. We have, what else do we have? 10-8-6-6, 8-8-8, 10-8-6. Is this one correct? That would be hard to check now. It is basically after 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 steps. Then we're saying we're turning right 8 times. So 10 steps I said, right? So that is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then I said we're going right 8 times, but it looks like 6. So I think I made a mistake there. And that means that we have another pattern. So that is, which pattern was it? 10-8-6-6, right? So our pattern with green is actually a little bit longer. So it's like this. 10-8-6-6, 10-8-6, and here, where else? That was it. And then what do we have left? We have 6-10-10. We have here 6-10-10, 6-10-10. But if we would include also the 8, then we have 8-6-10-10. And here we would have 8-6-10-10. And here we would have 8-6-10-10. And that means that we can use the 3 8 in a rows from here, but then not look at the second one. So that is it. We have found some patterns. It is like this, and the red pattern goes till here, and this one is not relevant. And I'm not sure why I'm not drawing the pattern line on the right side consistently. Let's do that. So we have blue here, 8-6-6 and 8-6-10-10. That is it. Now it looks like all unique patterns. Okay, so let's give each of them a name. I'll use white. A, B, and C. A, B, and C. And those are going to be L10, R8, L6, R6, and L8, L8, R8, and C is R8, L6, R10, R10. Okay, those are our 3 patterns, and we're going to have to program the robot with those patterns. And how is it again? So we need to specify that the robot is waking up, and then it's going to require input, and we can provide input to it in advance, no problem. So first we're going to say the main routine. What are we going to run? And that is going to be visible right here. So all the A ones are the green ones. So A, and all the red ones are B. So B and B here and B here, and C is the blue one. So basically our input looks like A, B, A, C, A, B, C, B, C, B. That way. And I know it's a bit small, so I'm not sure if it is clear to see, but that is our main input. And I'm going to put the whiteboard out of the screen right now, because we don't need it so much anymore, except for getting this list. So I'll actually copy it here from the screen. A, B, A, C, A, B, C, B, C, B, A, B, A, C, A, B, C, B, C, B. Okay, so that is the main program, and we need to specify it. And that means we're going to input one item, something one at a time. So I'll just take this as a string. Main equals this string, and for every character in main, we're going to input it, and we're going to give it the ASCII code like this. And that is the way it works, right? And then we need to specify a new line, and I can do that like this. And then we need to specify A, which is what was that again? That is from the whiteboard here. So that's a bit of a long function. I'll just read it from my whiteboard and type it over. L6 R6 with a new line. And B is another one. Oh, but actually this is not possible. This is not possible because I have integers in there as well. So maybe I'll just do computer.input and then just gonna specify everything by hand. Not so sure. Maybe I can do it like this. Oh man. Just thinking a way to do it quickly. Wait, no, what you were doing is fine. Really, I have to give the digits separately. I would think for moving forward I have to give an integer, right? Not ASCII. So we can provide, or a number, yeah, so that number will, oh, but will that number be an integer or digits? Ah, the number, well, okay, I guess as long as the number is less than 65, it means that it's not an alphabet. But I have 10. Well, how does that work? So the example is to move forward 10 units. Ah, I need to specify commas. That is what I need. Yeah, right. Okay. So I need to do it like this, and then it means that actually we do have fully ASCII as input, and we don't have to parse anything as integers or not integers. So that is what the input is going to look like. And then B is different. B is L8, L8. Wow. Wait, was that actually L or R? B was LLR. Okay. L8, R8, R8. Mistake again. So 2 L's, 1 R. Like this. And then C, another one. C was R, L, R, R. R, L, R, R. And the distances were 8, 6, 10, and 10. Okay, this is very error prone. I hope I didn't make any mistake, but we might be able to debug it with the robot, or actually to visualize what the robot is doing. Maybe. And how much time did we spend so far? We spent 1 hour and 43 minutes. That's already quite long, especially compared to part 1. Although I, of course, started half an hour into the day 17. So I was a little bit behind when I started. So this is the input, and we need to actually pass that to the computer. And maybe I'll just do all of it at once. So we're going to append all of those inputs. So it's main plus A plus B plus C. And then anything at the end? What was it at the end? A feed, whether or not we want something, and that gives us a continuous video feed, but it requires processing power and may cause your encode computer to overheat. But I think that is just a kind of joke. Maybe we can just say yes. Oh, you had a copy-paste error in your full path. Yeah, well, I had an error also in my path, and I realized it because I saw near patterns but not full patterns, and I thought probably there's something incorrect. And how did you find out that you had a copy-paste error? But if you couldn't compress it enough, it also means that you couldn't solve the puzzle. It's not just that you couldn't compress it, I suppose. You traced it back manually, yeah. I see. Another time, one more time, the boring stuff. Noch einmal. Alright, so we are running the computer and we're going to tell it also to please give us some output. Yes, small letter. That's it, and we're running it and then see what happens. Let's see what goes on. Well, nothing much, I would say. We have a big loop for the first section, where I still have a little print statement that is really not needed. And then we are done. But why does our computer not run all the way from the start? When I'm loading a program, I do call the load function, and I do clear the positions, and I do a reset, so our instruction pointer is back to 0. The input is cleared. I did overwrite position 2, position 0 actually. So, but maybe we should print. Maybe we should print. So let's call it print grid, like this. No, why should I print? I think the robot was supposed to tell me something. Maybe the robot will tell us what is in the output, what he saw on the way. Maybe we can actually break and have a look, or print. Let's print done and then break there. Well, so far my computer is not overheating. My brain is overheating though, quite strongly actually. Print done. And it's overheating because of too much thinking and not enough sleep. So we're done, and we have a computer, and we can look into the computer. And the computer is somewhere here. Yeah, if it does give you a visualization, that is great. Yeah, okay, it does actually. So that means that we can, let's say we have a grid like this. No, we first need to actually no, my robot is not asleep. I woke it up, I think. It's working. I am still asleep, rather. No, the robot is running. I overrode the second. I overrode memory position 1 with value 2. And that should make it awake, I think. Yep. No, that's fine. I always appreciate people asking me for double checks, because I might miss such things. So I just want to see how can I print my grid. Maybe I can just make a function called runRobot or something, which will return nothing. I'll just use globals, why not? No, actually I don't. Why do I even need to print anything? I don't need to print anything. I just need to get this output value, right? Let's just assume that this is all working. We're printing and we're done, and then we get one output value. And that is, what is the output value? It's a huge list. So, apparently it's still outputting a lot. Maybe we can evaluate the output and look at only the last position. It says 10. 10 is a new line. So that is definitely the fact that it's printing something. Okay. And if we specify no, then what would happen? So I'm now a little bit confused about if the robot would output anything at all while it's running. So let's see. Normally it wanders randomly, but now it doesn't. Yeah, so in the first part of the puzzle I just run the whole robot and it says it's walking randomly, but no, it's not. That is kind of incorrect because it's walking exactly on all of the scaffolds basically, perfectly, until you get all of the scaffolds. So with the standard position it's not walking randomly. Provide either Y or N and a new line. Thank you. I need to provide a new line also. But then what is it doing anyway? If now I get a number. Wait, but what am I printing here? That is something unrelated actually. So let's print the computer output and then the last number. Yeah, it's again a 10. What's wrong? Provide either Y or N and a new line. So yeah, I did fix that one, right? Are you sure input taking a string will work? No? I'm not sure about that at all. It doesn't. Yeah. Oh, okay. Thank you. Thank you very much. So now I pass it a 1, and actually even a character doesn't work. So there are multiple things wrong with this. I need to do it like this. Yeah. Okay. We still get 1 though. What about all those commas? Function C, A, B, and C. That would make it like this. You cannot... Okay. It's collected as a large non-ASCII value, so it should be large, and what I am getting is definitely not large. Very small. Maybe it's something to do with this position thing? No. Would make more sense if the first input was actually like if this override was also an input, but it's not. Maybe it's not the last, I don't know. Maybe it's not the last. But I am telling it not to give me any fancy output, but it's still doing that. So why? Let me actually run the debug. Run debug. See if it's waiting for input. Oh man, this is huge. Can I pause it? I can press stop, but I cannot pause it. But I can add a breakpoint on the fly, right? No, because I have no more statements that I could break. So I'm stopping it and looking. I'm running it for like a very small time. And then looking if I have an input array that is being read. So thanks for checking that. So my input array is here, and that also has character 110. I'm not sure what that is actually. Maybe that is wrong. It's an N. Oh, okay. So that is my last character. My N here, where I'm saying please don't. And then it should take input, right? but it looks like it's not really taking any input. All it's doing is increasing my... Maybe he's saying an error message. No way. No way. That is a joke. We have a relative base that is very huge. Is this my first output actually? No, yeah, I'm not sure. Okay, let me actually break the program. Let's go over it part by part. Okay, that was a joke. Good. There were error messages for you. Yeah, now you guys are messing with me. Well, let's see. Let's go over the execution loop and go one by one. So our console looks like this. And that is the first time we're running the robot, and I don't want to break there. I want to break only at the second point, like here. And our int code computer is here. And where is the instruction loop? Loop. Let's do it. So we run it till the first breakpoint. And then once we hit the breakpoint, we're gonna iterate over every part like this. Ah, that was actually day 5, I see. So where are we right now? We are now here. And then we are in the execution loop already. Is that correct? Yeah, I guess so. Okay. So after running one loop, what do we get? We didn't print anything yet. Why don't we print anything? It's doing a lot of things, but nothing is being printed. For example, if you use an integer in main, you get expected function name, but got 1. Wow, that is pretty cool. So it means I should really output everything what I'm doing. And what happens here at this point? We have inputs. No, we have no inputs. That is very suspicious. I am providing inputs before running the program. And I don't override anything there. I do load, and load does a reset, and reset does clear the inputs. Oh crap. Okay, so my inputs are actually not being saved. So that means I can do... I actually have to specify my inputs in advance. So let's do that. And let's append to that. So instead of computer inputs, we're going to just do inputs.append, and then we run it with those inputs. Run! Okay, maybe no debugging. Pause. And rerun it. Do we get a large number? No, 10. Again 10. So then debugging again. But debugging mode should be on, or maybe it doesn't need to be on. Maybe I can just have a look here and see the inputs. It's again an empty list. And we ran it with inputs. That is right. Well, maybe it's not running the first section, maybe it's running the second section. Oh, sorry, the other way around. So now we should get the second part, and then we can actually go into that and skip. Go into the execution loop. Now we are running second iteration of the robot. And after one iteration, what do we have? Respol, you solved it. Nice. So with a bit of manual and automation, human-computer friendship, you managed to do it. Okay, so this is our first iteration, and what do I actually print here? That's actually from the first part. So I want to know if we have input. Do we have input at this point? Inputs. Yes, we do have inputs ending with character 10, which is a new line, and then 110, which represented no for having special output. Okay, and let's watch also our inputs. I'm going to add that here as a watch variable, self.inputs. Now we should see that list being popped one at a time, at least soon. So the first item is 65. Let's run it a bit and see if that changes. No, nothing is being changed. And yeah, I feel like this is just gonna keep going and not reading any inputs. But is that maybe because the position that I'm overriding is not actually being overwritten? So we're loading it and then running it, and positions is replaced. And when I run it, I don't load the program because I don't specify the program. And I do specify inputs, that's it. Okay. So it seems like it's not reading my inputs at all. I'm going to run everything until the end and see if really no input is being read. If so, I don't know why it's not reading inputs. Then maybe the sleep is still not working, or the waking of the robot. So the inputs now look like computer inputs. It's an empty list, so actually it did read all of the inputs. Now the only thing is that it seems to not handle my output correctly. Maybe I can actually print the output. Maybe it was not a joke. Let's actually print it. For C in computer.output. Ah, yeah. Why didn't I take that hint? Come on. Like Emmy has said it and Alex has said it. I just didn't take the hint. And no new line. And then let's just run it. Oh, we have an X. Look at that. Oh, and it's saying main continuous video feed. It's printing something, but it's saying nothing, as if it didn't recognize anything or something. But we are getting off the track. Why are we getting off the track? Man. It looks like my input worked, but how do you see that? Because I don't see, it's not printing anything. It's just saying main and A and B and C, and it's not telling me that it's parsed it or something. It's only printing what the robot says. Okay. Yeah, but it's printing also this, so the robot is parsing something. Not what you tell him. Okay. Ah, so it's printing main, and then I have to provide input. Then it's saying function A, and I have to provide input and so on. Ah, so, and I'm not doing a interactive loop, and that's why I just get all of the questions and at once. Yeah, I see. Okay, well. And I'm falling off the track here, and that means that I'm going here. I think I come from, where do I come from? Just, well, it means that I'm coming from the bottom if I overshoot there. Another of our friends has solved it. Fuzzy, good job. Still a few more people to go. Most notably Hans and myself. And one of my colleagues, Yo, who is on the board. I'm not sure if he's watching right now, but he's definitely working on it. Nice, Fuzzy. We are not gonna give up. You had it done for like half an hour, just failed to print the answer. Oh man, really? Maybe that's what happens to me also. But I am coming from the bottom and I'm overshooting, and I have to go up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But I never output anything other than 10. Do I? I have 10. And what else? I do end up all the way here, so it means that I'm doing it right many times already. Is there any other way where I could have overshot and ended up here? I don't think so. I'm not really sure if the robot will still wander in space. Maybe it will wander in space. What does it say? Big X. Uncontrollably. Okay, so actually it could be that it doesn't actually fall off right here. It will just continue tumble uncontrollably, and it might be at any position in space, I would say. I wouldn't rely on it. So if we actually provide yes as the answer to the detailed feed, then what happens? Do we actually get something better? Well, it takes a long time now, and that is maybe because I'm not printing the output as it goes, and I don't have an output listener. That is kind of bad. I could add that quite quickly, I think. Let's say that we initialize the computer. Do we have a parent? Yeah, we can call a parent. Maybe I'll just attach an output handler like computer.output handler equals lambda, which gets a character and prints the ASCII version, like the actual character of it, without a new line. And then every time we need to output, we do it. Yeah. And this is probably going to give so much output that it's... Oh, I can scroll back all the way to the start, so that's good. Yeah, I like event handlers, but they're hard to debug, but they do work nicely. So we go left, and then we do one step and another step and another. Oh man, it's doing every single step. Oh no. Oh man. Okay, then it goes up. Yes. Yes, yes, yes. And then... Now where are we? We're down. Okay. Going to the right. Yeah, down. Okay. Now we're going up. Oh, we're actually going up. Okay. Ah. And then we're here. I'm not sure if you can see this. It's not that clear at all. Maybe I'll just print a character. What should I do? Like, if the character is... Well, okay, never mind. I was gonna make it red or something, but we're almost there. So I'll just try to show you where I'm looking. So here we're actually going up instead of left. So that means that there is a little mistake here. That is actually the part where... which part is that? That is section 1. So we have a direction and a magnitude. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and then the 14th instruction is wrong. And we can look at our instruction list like this. Right? And let's look at instruction. Oh man, which was it? 13 or 14? I forgot. Please let me know in the chat. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh wait, those are the main instructions. And then we have the steps, of course, and the steps are another thing. Yeah, I'm not counting the instructions indeed. So I remember that position 10 I already marked. It was this one. And we have 11, 12, 13, and 14. And here I'm saying probably it's this one. I'm not entirely sure. But it goes right, right, left, right. But it should go right, right, left, left, do you think? Ah, okay, so you mean this one. Or actually right, left, right, right. Well, depending on where you start looking. Let me just count it one more time. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So after the 13th step we are here. So step number 14 is where we do it wrong. And that is this one indeed, the one that I highlighted. So that means that that one actually goes to the left. Okay. So we might need to make a lot of corrections if that means that my patterns are wrong. So this one is left. And my C pattern. Oh, my C pattern was actually like here 8, 6, 10, 10. And right, left, left, left. Yeah, I had only looked at the distances when I looked at the patterns and not at the directions, funnily enough. That's how I didn't realize it. And here at first, we do have left, right, left, right. Oh no, that's a different pattern. And here we have another C, which is right, left, left, left. And here, oh, that means that this one might also be wrong. I think, unless I just broke it up completely wrong. That could be. So that is actually from the last step a few backwards. So let's see one step back, 2, 3, 4, 5. Let's see if the 5th step actually is a left turn or not. You think the first C is wrong? Okay. Let's see from the left, from the end. 1, 2, 3, 4, 5. So the end is here. 1, 2, 3, 4, 5. So that is a left turn. So that looks correct. And you think the first C is wrong. So that means it's step 11. And on my note it says it goes to the right. And step 11 I think this was step 13, 12, 11. And it says that it's going right. That looks fine. Oh, maybe not. Now it says it's going left, 6. I'm also a bit confused about when a segment starts, and I try to do it like always a turn and then a distance and not the other way around. So let me count again. You know what, I'm just gonna verify. But wait a second. Well, what the robot tells me is that even if my patterns are wrong, I do end up all the way here, right? So all my instructions that I'm giving are correct up till there. And that is the first time I'm doing a C pattern, so A and B are definitely correct. And my C pattern should just, oh, maybe, yeah, it should end with the left. So I'm just gonna change it and see if that fixes it. So it's right, left, right, and then left 10. And just see how it goes. And I want to have an output handler like this, printing a character every time. And the output handler will be used when we are doing an execution loop. And I think I don't have an output function, I'm not so sure. Output just appends something. So we'll just print, we'll also handle it then. So if self.output handler exists, then we're going to call it output handler with the value. And I just want to initialize it with nothing. Output handler. Yeah, and I really don't know if I should clear it when I reset or not. That is definitely not clear. But I guess I can always override it if I need to. There's no kind of bad side effect most likely. So let's not print everything at the end anymore. And let's run it. So now we get the feed. That's pretty cool actually. It does take a long time. Where is it actually? So right now it's still going on the first part, going up. And can I still print the character a bit more clear? So if the character is in this list of directions is a string with those angles, then I would like to print the character with red around it. And red was done by, I'll make a little function for that. Red is a lambda that takes a character and then returns, or maybe I'll call it draw robot. That is basically this function here. Like that. Lambda with a no, not exactly. It takes a robot as an input, or a direction rather, but dir in this case is an offset and not an actual angle. So maybe just this part. So let's just return it like this. Yeah, that works. So basically it's actually drawing something in red. So I'll call it red. And then here I'm going to draw it red if it is in the direction, so it's a robot, and otherwise I'll just draw the character itself. And then we rerun it. But actually red doesn't print anything in red, so I need to use a different value. I think it's something like 42. It's not, but it's kind of clear. ASCII red. Let's see. Which ASCII code is red? Oh, I should write ANSI actually. Red. That is 41. Okay. So I'm not sure why that didn't work. Foreground code 31 actually. Okay. Yeah, now we can see it more clearly. Okay. So we're going to run this until it crashes or until it's done. I actually suspect that I fixed the bug and that it was finished till the very end and I have the output, but I didn't look at it. Wow, this makes me feel a little bit nauseous, so I'm not gonna look at it while it's running. Maybe I can make it a bit smaller. Yeah, this just takes a long time. Going to the left and going up. Now we're finally at the point where we fixed some bug. And it doesn't quit. It does quit. So it goes to the left and then goes to the right. And so there is still really something wrong. And Emmy, you're saying that you think my C pattern is wrong. Well, if I think I'm off by 1. Yeah, so it's probably that we're starting with going left. Yeah, so the pattern right before it is an A pattern, which means that we ended by going right 6 times. And I think that was 1, 2, 3, 4. No, it's also not right. So we went to the right. Yeah, but I don't know where my C pattern is starting. That is a problem. And my previous pattern was A, which was 10, 8, and 6. So that looks like... where is my section of 10 long? Maybe here? No. If you print the output non-verbose, it will show you the ending position, whether it fell or not. That's interesting. Okay. I will use that maybe at some point. If it's the position like the XY coordinate, it wouldn't be super helpful, but if it was the actually instruction position, that would be helpful. So maybe I can run it like No. Oh, it shows you the full map. Okay. Ha! Oi? It's different. Oh yeah, because I was already changing things here. So maybe I can just do it like that. So I'm going to go left 8 steps. 1, 2, 3, 4, 5, 6, 7, 8. No. So maybe this is the start of an A pattern. So we went left and then went down. No, also not. Good morning. I still don't know where we are. So let's say we have A, B, A, C. No, no, that's wrong. I'm counting it wrong. I fell right at the beginning of the C pattern. Well, but now I see an X here. Oh yeah, okay, so this was actually right, going 8 to the right, going left 6, then going down. I changed the wrong one. I should go left and then 10 down and then 10 to the right. Yeah, like this. Okay, I think this is probably going to be correct. Yeah, okay. And what is the output? A special character that I shouldn't print. So that means I can now print the last one. Let's see, computer.output -1. Okay. Okay. 790595. I think that should be it. Yes, it is the right one. Yay! Woohoo! Okay. Let's see. Okay, well, we're done then. Okay, well, very good. Thanks for helping me out here. That was very helpful and handy. If I just look back at what we were doing, look at this crazy sheet. This is like really insane. It's so boring to do that. But we managed to figure it out and we got the puzzle solved. So I'm going to take a little bit of a break, just a few minutes, because I'm very exhausted. And then I would like to spend maybe 20 minutes or so of going through other people's solutions. That would be fun. And then I'm going to end the stream today so I can actually go to work sort of on time. Maybe just a tiny bit later than usual. And Valerie just solved it right in time for the break. So have a good break for a few minutes and see you in a moment. Hello everyone, I'm back. Back to have a look at some of the solutions that other people have made. And by the way, I have good news. My girlfriend just told me that her abstract was accepted for a conference in San Diego in March. So that means we're gonna go to America, and that's super much fun. Very much looking forward to it. Very happy news. She just told me about it. And so I'm happy for multiple reasons, and that is one. And of course, solving part 2 of day 17, that is also a great news. But one I wouldn't remember as long as a trip to the US, of course. So, Alex, you're saying you solved both parts manually and part 1 partially, but you have now written a function that does part 1 and gives you the whole sequence for part 2. But splitting it into functions you did manually. I see. And you have a paste bin for us to look at. Okay. Yeah, it's so cool, right? I have been to the US before. I've been to LA and I stayed there for just a couple of days and I liked it very much. So it's a similar area and I'm looking forward to have a visit to LA again. Maybe I can this time visit some kind of cool tech companies or join some conference. I don't know what's going on there in March. We'll have to look into it. It's been 5 minutes knowing this news, so haven't investigated the options yet. So Alex, I'm going to have a look at what you did. So you have your VM as usual, and checking to hear if we still have music. Yeah, we have music, but it's very, very soft. Just gonna change that. Okay, that is a little bit more loud. So we will make a little file like that. Alex, oh, I just made you into a package. I'm sorry, man. I will make you into a Python file instead. Here we go. Copy all of that. Maybe I can just do like raw and then copy. And I saved it. And okay, let's see how we can run this. The VM is there for us to use, and day 17 has an input. Okay, so how shall we do it? Shall I just go over it and read it? Or do you have something you want to add to it yourself that you might want to like say live or on the chat? It's not very big actually. Yeah. Okay. So we are reading the input file as usual, and we have a dictionary with the grid, I suppose, and you run it until you run the VM until it stops, and then we read actually all of the characters, and that's similar to what I was doing. And you are using, yeah, okay, so every time you get a new line, you're resetting the X position and increasing the Y position, and otherwise you're reading the direction from the character. And if you're actually one of those 4 directions, then you're going to map every character into a certain direction. Yeah, that is also a nice way to do it with a dictionary instead of a list and using the indexes. And otherwise, if you have a hash, then you do have a 1 in your grid. And that's the only place where you're actually updating your grid. And I suppose you're doing that because you want to keep track of where you went, or maybe this grid just represents all of the scaffolds. So you have commands, and you have a list of visited items, so that probably you're going to do some kind of search algorithm right here. And oh, so you have the X and dy, but where do you have the X and dy defined? The X and dy, I guess, that is actually the vector, like split up for the robot in which direction it's facing. So you have the robot's position, which is basically the X. I see what you're doing. Okay, so the robot has a certain position, and you want to know if that position is going to be available. So if there is a 1 in that position, and because you have a position, and at the end of the loop you are going to update the position, and you want to know before you go into the next iteration if you're actually not going to land on space. So to do that, you're calculating the future position by taking the robot's X position and adding the X, and same for Y. So then you know that you're not going to jump off of the cliff. And then if you did that, then you're saying that you count an extra visit to the location where you are right now. And you have a list of commands also, and you're checking that your commands, the last item in your command is an integer. And why is that? And also you're appending 1 to the list of commands. You're adding 1 to the last item in the commands. So now it's the challenge to figure out what commands is for. You're appending, and I think what you're doing, I see what you're doing. So basically you say, okay, I need to go forward, and I go forward 1 step. And then if you can go forward again, then you're just updating the last command and say, okay, I'm just going 1 more forward. So you're not kind of tracing directly to the position where you need to be, but you're going step by step as the robot would do itself also. So here you're checking actually if you've already initiated a command, and that means that one of these other cases has happened before. So for example, you went, you decided that, let's see, you can turn either left or right, and depending on whether you turn left or right, you end up here or here, and you're using the same kind of coordinate flip as you did before to calculate where you end up. And so to turn left, instead of adding the x as you normally would when you increment a distance or like update a position, you're actually adding the y, and then to update the y position you're subtracting the x. So that is a left turn, and that works for any kind of current direction that you're currently facing. So this will always give you the new position of the coordinate where you would end up after turning and then going forward. Yeah, and so once you've decided that you're gonna go left, you're appending it to the list. That means that if you're calculating the run length of how far you're going to go forward, then you only can do that when you've already issued a turn, because this puzzle does start with a turn also. I'm assuming that this is the same for everyone. My robot faced up, but the path was actually going to the left, so I had to first turn left. So then if you're issuing a command right now, no, hold on a second. This is actually just checking if there are any commands at all. And here you're checking if the last command that you're working with is an integer. And if it is an integer, it means that you were actually working with a direction and you've already added a certain distance. But what I'm missing here is that if you're going left and you know that the position you're going to go to, you could basically already say, okay, then I'm going to go forward by 1. That means that basically this code would be here. And then if that is the case, then you basically can always assume that you're already in some kind of command and you're already having as the last position an integer. That would just basically move around a bunch of lines. And it would, I think, be equivalent, but I'm not entirely sure. So if the last one was actually an L or an R, then you're appending 1, so you would go forward at least once. And then the next time you're passing here, you see, okay, we already have a number and we can just increment it by 1 because this direction we're going right now still has a path in front of us. And that is how you determine the list of commands that you need to issue. And so you have now a list of commands, and let's print them. Let's print it right up till here. And see what kind of commands do we get. So here you have the full list, and then you issued, then you looked manually at it to see if there were any patterns in there. And I know that it's called the largest common substring, or largest common, not subset. I think that is the problem that we're actually solving. Largest common substring. And if you would apply that algorithm, if you would know it, for example, you could find reoccurring phrases. And I don't know the algorithm for that. Probably it's some kind of dynamic programming thing again. Yeah, of course. Where you keep partial solutions and creating tables and stuff. And your longest wasn't actually a function, because there might be a repetition in there that is so big that you can't repeat it enough times so that you would be able to solve the whole puzzle with just 3 patterns. And isn't there some kind of online tool for this? Online find common substrings. These days, you know, you don't have to program everything. Between 2 pieces of text. No. I want to find the common substring within itself. So maybe that's a different question I'm trying to answer. And you went, Crispus, you're saying you went down that route a bit before you realized you were working on a mistyped string. Yeah, that is such a waste of time. That's a shame, but well, you did solve it in the end, and that is of course what matters. So here we have an example where we have 3 strings, and then out of those 3 strings we find a common substring. So basically what you can do is to pass this string twice. I cannot find my page anymore. So let's do it twice and see what we get. No, we get just the full input. I am curious kind of how to quickly find those patterns. I think you can do it. I think you can do it by brute force. You don't have to make some kind of smart optimization. And you think we're lucky we never had to split ints into 2 ints and to see the patterns. Yeah, that's actually, you mean like 12 being composed of 1 and 2. I'm very happy that we could just pass full digits and not kind of think about that. So that's nice. And you're also kind of combining all of the input, and then you're going to give it to the robot. And how did you define A, B, and C then? So you know all the commands and they are here. And then, okay, so you made this manually. This is actually the different inputs. I see. In Fuzzy, you thought it might be the case, and it slowed you down a bit considering that option. It definitely also slowed me down for a bit, but luckily I had you on the stream, and someone helped me to kind of avoid that route. Like R8, R12 becomes AA4 with A equals R and 8. Oh, I see. Okay, so actually that is also possible, that you would actually decompose the distances. Oh, wow. That is actually another way to do it, and it would technically be possible. I think this code, this int code program that we got would be able to support it. But yeah, we're lucky that all the distances were kind of full patterns and not like made of several patterns. All right, and also the subcommands were just basically, no, they were not simple instructions. They were a combination of instructions. It did say the main program could have only A, B, or C and not directions or anything, but you could have an A that went like to the right and then forward and then to the right and then forward, and then another one that starts by going forward, and then yeah, you could not actually understand very easily what's going on. Yeah, exactly what Alex is saying. The 4 could be part of the next pattern. And then when you pass it to the robot, you basically just you give it the data, and then on output you're printing it. And if you have more than 255, then it's not ASCII, and then you're printing it. Right. And then add out CB, that's the callback that you're using. And you're sending it the inputs and giving it all of the ASCII values, and it runs until it blocks. Cool. Okay, let's see how much time I have. Well, I have not a lot of time. But does anyone have a solution that we can look at? Please go ahead. I'll do one more before I end today. And in the meantime, I'm also curious, how do you actually get the patterns? So let's say we have a string S and it has a lot of numbers. Well, maybe I should just use the pattern that you found from the output. So that was this one. And let's do it in the console. So those are the patterns, or the instructions rather. Now we want to find all of the occurring substrings. So let's try the different lengths, such as from 1. Well, maybe I should split this up into separate instructions. So s dot split by comma. Now we have it like this, which is fine, I guess. Okay, now we're going over different lengths for different lengths of patterns, and we start with a length of 1, maybe. Well, let's start with a length of, yeah, okay, 1. And then until the maximum length, which would be, like, let's say half of the string length, divided by 2 without any remainder. And we're going to try out everything, and we're going to iterate over the string and counting how many times each pattern occurs. So we have, we're going to, let's see what we're doing. We're going to iterate over the strings positions for p in range 0 till length s, and then we're gonna see if in s at position p until l, that is like this, that is the substring that we're finding, and we're going to count it, and we're going to save it into default dictionary. So the pattern counts at this particular pattern is going to be incremented by 1, but of course we don't have pattern counts yet because we need to import collections. I guess actually I will make a little Python file, and we call it patterns, and then I can run this there. I think it should not be too hard to find those patterns. Pattern counts is going to be a default dict, like that, which returns a lambda by default, so we can actually just add one even if we don't have a value there. So s at position, and then the s is this list that I got from the console. This one. Just need to clean it up a little bit. No, actually that worked. So it's not copying those angles for some reason. That's great. And then we have all the pattern counts. Let's just print. How should we do it? Maybe we can sort it. Maybe we can... I would like to print it sorted. So let's do sorted of items. And I think that should sort it by ease, but I want to sort it by values. So wait, it's actually the pattern counts. And we sort it. And can we do a key or something? Yes, we can. It's a lambda with which receives an item, and we're going to sort it by the count, and that is the second one. And then I want to do it in reverse. So maybe we can also say descending or something, or direction. Not so sure. No, we cannot do that, but we can do minus item and it would sort it the other way around. And why does this not work? Because lambdas don't have a return. It just looks like this. And that is all the items, and then we can print them. Maybe list patterns, because I think it gives us a generator. Unhashable type list, and where does that happen? That happens right here. So I am taking a string which is a list, and I want to kind of make it into a pattern. So maybe I can first turn it into a tuple, so it will be hashable, like that. Now we have a list. Let's just go over all of the patterns. Pattern and count in patterns, and then we're printing the pattern and the count. Pattern count, like that. And hopefully it's sorted also. Oh, and I need braces for the print function. Now we have all the patterns and how many times they occur, and many of them occur not so much. So 52 times just the letter 8 or the digit 8, and then we have a bunch of more. Now the question is, of course, which patterns can you use to completely define all of the input? It makes sense to start with the largest pattern and then trying the other ones, right? So I think you do need some kind of search algorithm for that, because just having all these patterns is not going to help. But we can filter out all the patterns that occur only once. So for example, if count is 1, then we just skip it. Then we should, maybe I'll just filter it actually. So patterns is P for P in patterns, and if the count is bigger than 1, then we're going to print it, and let's see how much we got. We get quite a bit. And well, so we have some patterns that are really large, and I think that's what Alex was saying, that you did find a very big pattern being repeated, but it's not the one you used finally in the output. So yeah, those are all of our patterns, and now to know quickly which ones you need to use from those, that is not so obvious. I think you would just start, yeah, you would have basically patterns to try. That is a list of all of the patterns that we still have, all of the keys, and we're going to need to check the upper bound of P. It depends on L, the upper bound, and that's what you mean by that. Okay, I cannot actually go till the very end. Right, you are right. So it's minus, so we go from 0 till the end of the string minus the length of the pattern that we're checking. That helps. Yep. So now we get less patterns, I think. Not sure. It's different anyway. And so if we have patterns that we're going, actually what we're going to check, I'm thinking how we can actually implement it. So for this stream today, I will just try to figure out how to calculate all the patterns, and then I'll end the stream. So no review for today. But I think that probably we have solved it in similar ways, and I don't get any suggestions today, so that is totally okay. But then I'll just stick with this one. So basically we have our input like this, and we have a bunch of patterns, like a small one, a big one, another one, and then we're going to try first this one, and then let's see if we can continue with another one. And I just realized that we can only pick 3 patterns in total. So basically it's not so many combinations, I think. Well, maybe it is a lot of combinations. We have how many? Print length of patterns. So I was just thinking, what if we try all of the patterns, all of the combinations of patterns? We have 262, and that means that the total number of combinations is 226 for the first pattern, 225 for the second one, and 224 for the third one. That is 11 million combinations. That is quite a lot. And so probably that is not gonna work. To brute force it, I mean. Well, if you want to wait 10 minutes, probably it can be brute forced. And so what we need to do is try out a pattern. Basically, we need to start with a pattern also. So every pattern that is not any pattern that you do not see at the start is basically an invalid pattern. So I'm going to filter those out as well. So patterns, another pattern for P in patterns. Only if the first string, the start of the string from 0 till the length of the pattern. This was a count actually, and here we have a count. So the length of the pattern, that's what we need. So let's say the pattern is 1 long, then it goes from 0 to 1, and we have 1 character. So if, well, maybe we can even do starts with, no, on a list. That would be cool if that could be done actually. No, but we can easily compare, like like this. If that is equals the pattern, then we're good for that particular pattern. And why does this not work? Maybe like this. So now we have some other patterns. And I see some chats coming in. I'm going to read that in a second. Here we need to run it and we get 0. So the max length of the string is 20. Could help you filter them. So anything with more than 10 elements is a no-go because you have the commas. Oh, but I'm splitting the commas, right? I'm splitting on commas, so I don't have the commas in the patterns. Max length of the string is 20. Do you mean the max length of the patterns, or maybe you can clarify what you mean exactly? And so this didn't work. The pattern should be exactly P, but I'm not entirely sure that works. Let's break here and see what happens. So we can evaluate, let's say, patterns. The first pattern that we see, that is the 0, that is L, only consisting of L. And the next one that is a bit longer is 8L. And we have also L10. Let's start with that one, because it starts with a turn. It occurs 9 times. And does that actually match, does the first position there, the pattern, does that actually match with the start of the string? So from 0 till 2 is not true, because the string starts with L. Oh, the string starts with L10, but the pattern, how about the pattern? It's also L10, but one is a tuple and one is a list. Well, maybe that's the reason why it doesn't work. So now we have 2 that should be the same, and when we do it like this, it's true. So we should actually check within the string compared with the tuple, otherwise Python will recognize it as something different. So our, oh, that still didn't work. And the pattern, was it actually the pattern perhaps that, well, maybe we should do both as a tuple. I don't know anymore. Let's run it. And now we get 14 patterns that are possible. And Fuzzy, you're saying, so anything with more than 10 elements is a no-go because you have the commas. Each of A, B, C is limited to 20 characters. Ah, so you can't use anything longer than 10 elements because that's 9 commas and a maximum of 10 digits. And some digits might even have more than 1. Or some numbers might be 2 digits even. So that is a good upper bound indeed. So I will make that also. So all of the patterns, we can go up to halfway. We can go up to halfway the length of the list. And we're going to take the minimum of 10 and those. Right? Yeah. So now we get another list, and it's only 9 left. Well, 9 is something you can try, because 9 times 8 times 7 is 504 different combinations of patterns. And basically all we need to do is to try out every pattern and then try the other 2 and see if it works. Or 10 other values including R and L. Yes, exactly. So at this point we could actually start with any of these. Oh, but hold on a second. Those are only the valid patterns to start with. So that doesn't mean that the other patterns are invalid. This is basically our pattern validation algorithm. So what it means that we must use one of these patterns. Yeah. Starting patterns are like this. Pattern is valid is how we check it. Let's see how we can do it. Yeah, I think what you basically need is some kind of stack because you kind of need to pop, you need to try out different options and then pop. So basically, if you're just appending every next pattern to a stack, not sure exactly how I'm going to solve this, how I'm going to do it algorithmically. So let's say we have an eternal loop, and we're going to pick a first pattern to try, so that it comes from the list of patterns, and we're going to keep as the current pattern is this one, and we're going to pop it from the patterns, and then we're going to see if the current pattern matches with the position. And our current position is 0, but I think we need some kind of stack also. Maybe we start with position 0, like this. And then we need to check from from position P to position plus the length of the pattern, and if that matches, then we actually have a valid pattern. Right. I think you put that upper bound on the wrong loop. It should be on the inner loop, if I understand your code correctly. I'm going over all the different lengths of patterns. So I'm trying every pattern, starting from a pattern that is 1 long, up till at most half of the length of the string. Actually, that is technically not necessary. I could go even all the way till the end of the string minus, like, let's say 4 or something. Actually, it's not even necessary. So we can have a pattern that is as long as the input string, except for the upper bound that you mentioned before. So that's why I have -10 here. And here, this is actually slicing, moving a window through the string. Yeah, so here we're moving that pattern across the string and counting them. And so I feel like this is basically a search algorithm. So it should be the same as every search algorithm we've done so far. And that consisted always from of a few things. It consisted of to visit and visited, and with visited you keep a track of what you've tried, and that would basically be a path, a list of paths that you've tried, and to visit would be a starting path. And we might start with a path of nothing, which means we have not taken any pattern yet. I guess that's what we do. So it means we start with offset 0 and no patterns. That makes sense, I guess. So it really helps to just write it in the same way as every time. So we have position and patterns that we chose. Okay. And patterns is actually going to be the... Well, it's not the whole list of patterns, it's only the list of patterns for this particular configuration. So, well, let's call it selected patterns or something. And so those are the patterns that we selected, and we might want to also keep a list of which ones we applied in which order. I'm not entirely sure if we need to. Maybe we do need to, because we can say we figure out that we are using pattern A, and we're then at position 3 or something. But what if after that we apply A again, we're at position 6 and we have A. We still picked A as one of our patterns, but the path we took is AA. So that's something that we can keep track of separately. So that will be the path. Yeah, the path, which is basically a bunch of patterns in a row. All right. So while it's true, then what we always do is checking the next possible steps. And the next possible steps are trying every other pattern that we haven't tried yet. So for every other pattern, so for pattern and count, the count is actually not important. So for pattern in patterns.values, and then only, well, so there are a few cases. If we have only selected one pattern, then we can just select a few new ones. But if not, then if we have already selected 3 patterns, then basically our search algorithm is going to have to use those 3. We can never add more than 3. So let's first handle the case where we have less than 3. Oh man, this music is very distracting. It's funny though, but maybe that... What is this music called? Ragtime? Might be not the most perfect music for solving puzzles. So I think my time is actually running out. Does anyone have a suggestion how to go on from here? So if we have selected patterns, we need to try them first. So let's say we are going to select 3. No, we're going to select more than 3. Okay, let's just try all of the patterns. Okay, so that means that toVisit is going to be appended. Our position is going to be incremented by the length of the last path on this list, like this. Then we're going to append one more option to try, and that is the one where the position is incremented already, and the selected patterns will include the pattern available, and the path will be the current path that we had plus the pattern that we chose. So after one iteration, we should have now a nice list. Let's break and loop over, or maybe just let's, what shall we do? Maybe print the toVisit list. Break is not possible. Why not? I'm in a loop, right? Maybe not. Maybe I have something wrong here. Yeah. Okay. Let's rerun it. List index out of range. That is because the path is still empty right now. So if we have no path, then our position is 0. That is correct. So if path, else 0. And we have no values because patterns contains only the patterns and no longer the counts. I updated that already. So here we have some options, and it's not super easy to read. So let's print it like this instead. Well, now it becomes clear that solving it by hand, just by looking at the code or at the puzzle, might be a little bit easier. And so here are all of the options, quite a bunch of them. Because I'm no longer stopping halfway the pattern length, halfway the string length, and anything goes really. And I see something, I'm not sure if it's the way I wanted it. We have a position, selected pattern, and a path. So we have a position, a list of patterns. I'm not sure that looks exactly right. I think I'm trying to append a pattern here, and maybe that is not going the way I think it should, or the way I think it does. So the selected patterns is an empty list, and we want to extend it with this particular pattern, which does have a count. That's surprising. I thought I already... Oh no, I didn't actually take only the count. I didn't take off the count. So maybe we can do it like patterns dot... okay, so we need to extract it like this. Then we would only have the pattern itself and not the counts. So now we get a clear list. So the first option is to use the pattern L. Okay. And then in the second iteration, when we don't break, then we're going to try out something. We're going to try out, this is an old watch variable I don't need anymore. We're going to try the tuple, the pattern L, and let's see if it is valid. So if it's not valid, we're going to not actually look for any children. So how is it valid? I had code for that before, but I think I removed it. But we can do that again. If valid, then we're going to populate children, otherwise not. And valid is valid when at a certain position in the string, namely the position and then till that position plus the length of that pattern, which is basically the sum of lengths of the path. Do I actually keep the last pattern that we tried? No, we don't. So it's basically the last item in the path, I think. Hold on. Actually, it's not so clear what we're doing here. I think, yeah, the last item in the path is the pattern we're picking right now. And so that means we need to try out if path, which contains nothing at the moment, is right. That's strange. Then why do we have a value called pattern here? Because now we're inside the loop. Well, there are two things you can do in search algorithms. You can either append only valid values, or you can append them and then check them later. And I think the best practice and standard practice is to append all of the children and then in the next iteration check if they are valid. I'm not sure exactly why. I think it has to do with if you're using A star and your heuristic function is expensive, then you don't want to evaluate every possible node to see if it is actually a correct node or not. You're actually going to evaluate each node only if it has a chance of being correct. Something like that. But that means that the last item in the path was the one that we were going to add, and we need to see if that one is valid. So the last pattern is actually path -1. But what if we don't have a path yet? Then what are we actually testing? We don't have a path yet. But we should have a path. Because we are doing the second iteration, don't we? Aren't we? No, this is the first iteration. And on the first iteration we don't have anything to visit. So maybe it's better to populate the entire to visit list with just all of the patterns. That is something we could do. So yeah, let's do that. So for pattern and count in patterns, and then we're going to have the pattern there and there. So 1 because it's part of the path, and 1 is because it's one of the selected patterns. And the selected patterns is actually a set that contains this single pattern in it. Okay, so now we do have a path in the first iteration, I think. And we say that it was valid. No, we haven't checked it actually, we just looked up the string and we have pattern L, but our string is starting with 1. Is that possible? We're starting with L and our position is... Maybe our position should be... I just realized that if we say that we went with pattern A, for example, then we cannot say that we're at position 0. We are already further away. So I think this is not the way I want to do it, but maybe we can. I'm not entirely sure. Let's revert it and start with an empty set and no path, like that. And then we just have a special case where we have no path at all. And then we're going to expand. So either we have no path. If we have a path, we're checking if the last pattern on the path was valid, and otherwise we're also fine. And in that case, valid is true also. And then we're going to go over the children, right? So for those of you who just joined in, we have already solved day 17 today, and it is a kind of tricky algorithm or tricky puzzle. We have a huge list of instructions to pass to a robot, like where to go, but we have to actually find patterns in that instruction so we can compress it. We can make 3 patterns, like let's say left 10, right 10, forward 10, and so on. That would be instruction A, and we can define 3 of those instructions and instruct the robot to go where it needs to go with those kind of macro functions. And so what I wanted to do is, let's say you have an input like this. This is your instruction list. How do you find 3 patterns that can uniquely, completely define the entire input? And we're doing a search algorithm trying out different patterns. So we start with nothing at position 0. If we have a path, we're taking the last one, checking if it's valid. And it's valid if that pattern occurs exactly at the current position where we are. And if that piece of text in that string or list is exactly the same as the last pattern, then we have a match. And I do need to make it into tuples because otherwise the comparisons are not going to work. And I might do a little bit too many tuples here, but that is not a problem. So if it's valid, then we're going to look at all of the children, and let's see how far we get. And then there's an extra constraint. We cannot add any new patterns if we have already chosen 3 selected patterns. So we need to look at the available patterns, and those are either the selected patterns if the length of those is exactly 3, and otherwise it is not all of the patterns actually. It is going to be the selected patterns plus 1. It's going to be any other pattern that is left. So that it will be patterns like that. So we're going to try out all of the patterns. And when are we actually done? We are done when we reach the end of the string. So if our position is the same as the length of the string minus 1, then we are done. We're breaking. And we'll say found a solution with the following patterns and path, this path. So the selected patterns are here and the path is there. Well, let's see if that works. Why is this red? Unresolved reference, selected patterns. But it looks like we do have it defined here. It is even highlighted. Oh, I don't have an else here. Maybe that is the reason. I should have an else instead of a colon. And here we cannot unpack enough values because we are doing available patterns and that one doesn't have a count. And otherwise we're going to do patterns without the counts. So that means the p for every p and count in the patterns list. Like that. Now it's running for a long time and we don't see anything. So let's also print out that it's trying a bunch of things. Path. Let's see. So it's trying a lot of things. And I'm also going to print the position. Like that. So it's going really far. It's still trying 10, but 10 was actually an invalid path. We know that already because the input doesn't start with 10. So maybe something is going wrong. Let's go and try the first part. First attempt that we're doing is trying an empty list. And we are actually in, no, we're not trying an empty list, we're trying L. And our list looks like it starts with 10. But that's the particular position that we're evaluating right now. But S actually does start with an L and then a 10. So this piece evaluates to 10, okay. But we are trying L10, okay. No, we're just trying L. How does that work? So we have S, looks like L and 10. We're trying out L, and we're starting with position 0, right? Ah, maybe that's why. Position should not be 1 yet, because we haven't tried it yet, I guess. Yeah, I think that the position should be added. Maybe later, maybe not here yet. So we're at position 0, trying out L, and that means that when we see that it's valid, then we should actually increment it with the length of the pattern that we did try, that we actually tried the previous time. That's a bit funky. Not sure if that is going to be very clear. And now we get list index out of range because we have no paths here. So let's add something like moved position or jump position or something. So if we have no paths, then we jump with nothing, and otherwise we jump with the length of the last pattern. Okay, let's see what happens now. We are going to see if it is valid. So our last pattern is L, and we say that it's valid, and the length is actually going to be 1. Okay, and then we're going to try available patterns, and those are all of the patterns. And then we're going to append a bunch, and we're going to append, for example, pattern L, and then the path would be something like LL. That is correct. It doesn't make a lot of sense to do that, of course, but well, the algorithm should be able to figure it out, actually. Now, I'm only not sure about my breaking logic. If the string length is 1 and we are at position 1, then we're actually done. So maybe we should actually... maybe we should add the jump to it also. And let's do a greater than to be sure that we're not going on forever and ever, in case we skip it by accident. And then we are not printing anything because it takes too long. It is really trying a lot of things. And I want to... the to visit is... Hold on. Visited is actually not necessary because we're not moving on a grid and we can't really go back. So that's not necessary either. And then I'm curious how many items are in this list. So let's highlight all of the commas here. And we have 71 carets, 71 commas. That means 72 characters. So we need to reach 72 actually. That is quite a big step, a big way to reach. So we were adding the length of the last pattern. Okay, that looks like it's correct. I'm just gonna remove this printing statement as I had, and then printing everything, and see if we can run it fast enough. Maybe I can do a kind of counter, like 0 iterations and then increment it every time. I plus equals 1, and then print something every time I is a multiple of 100, for example. Like this. And we're going to run it again. And maybe I'll actually keep the maximum distance that we've covered best is 0, and if position is bigger than, well, maybe best equals the max of the position, and best, and then we can actually say what is the best position we've reached so far, like that. So we are now doing position I, and we have the best and the path. Okay, let's see. So 22 is now the deepest level that we've reached. And that will go on and on and on. Seems like we're not really going any further. And you need to leave, and you're not sure if you can be there tomorrow because you're leaving for a Christmas vacation. That's awesome. I hope you're gonna have a great vacation, and of course, no one is committed to stay on the stream for 25 days, but I do enjoy the company. So see you again when you're back, and do enjoy your holiday. So this really takes a long time. There are apparently a lot of combinations. And we could use, of course, some of our logic. We could use some knowledge, like knowing, for example, that our patterns most likely start with a direction and a length, rather than a direction and then a new pattern that has a length. That probably wouldn't make too much sense. So, but that is basically using knowledge that we already have. But we can say that the pattern should be at least 1 long, right? Because just turning left, 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 this really doesn't make any sense. So the minimum length of a pattern is 2. And maybe we don't want odd ones. I'm not sure exactly. So let's see if it goes a bit faster. Yeah, not so much is happening at 6 AM. That is usually the case. Okay, well, see you later. And I'll be happy to see you again on other streams. So now we've reached position 31. That takes a long time. I think I'm also going to call it a day. Right now it's already way beyond my time I should leave. It means I'm gonna have to catch up or do something, or just make an arrangement. That's fine. Thanks everyone for watching, and I will try to finish day 16 part 2 maybe tomorrow morning before starting on day 18. We'll see. Yep. What else is there to say? Yeah, if you're new to this channel and you haven't subscribed or followed, please do follow me on Twitch. And I have a leaderboard. It's right above, and you can still join it. It's still open, but you need to have this private code. It's this one right here on the stream. Do enjoy Advent of Code and Christmas, of course. And I'll be ready again for day 18 tomorrow morning. If you want to see me solve part 2 of the yesterday, do come a little bit earlier and you can join there. You're very welcome, Emily. Nice that you're hanging out so often with us. Thanks, Graspel, also. See you. Goodbye.